Hey guys, yeah, so problem 5 here, and in part A we have to find the slope of the tangent line to the graph of f at x equals 3. So a nice summary of all of these words is find f prime of 3. So clearly they're checking to see if, all of them words in part A just mean find f prime of 3. Alright, now to find f prime of 3, we need to first find f prime. And I want to avoid the quotient rule, so I'm going to rewrite f prime of x as 3 times 2x squared minus 7x plus 5 to the negative 1 power, right? And then that way I can use the power rule and the chain rule to find that f prime of x is equal to 3 times negative 1, so negative 3, and then times 2x squared minus 7x plus 5 to the negative 2 power. And then by chain rule, we multiply by the derivative of the quadratic inside the parentheses. So that is 4x minus 7, right? Okay, cool. That's f prime of x. I want to write f prime of x a bit cleaned up, like with that negative exponent being positive and all that good stuff. So then that'd mean I write negative 3 times 4x minus 7 all divided by 2x squared minus 7x plus 5 all squared, right? Okay, cool. Now I could have distributed this negative 3 to this guy and this guy, but I didn't want to intentionally. I think it will make for easier computation and all that good stuff. Now what we need to do to find f prime of 3 is clearly plug in 3 there, there, and there. And when we do, it's easy to see that we'd have to write that what we have is negative 3 times 4 times 3 is 12, so 12 minus 7, and that's the numerator. And then the denominator will be 2 times 3 squared. 3 squared is 9, times 2 is 18, so 18, and then minus 7 times 3 is 21, so 18 minus 21 plus 5 all squared, right? Okay, cool. So the numerator is negative 3 times 5, and then the denominator is 18 minus 21 is negative 3 plus 5 is 2, so 2 squared. So that's going to say negative 15 divided by 4, right? Okay, cool. So that's f prime of 3, and that's the answer to A. And if you write everything I've written, that should be sufficient evidence of showing your work. Okay, now for part B, you've read it, so what it says is we have to find critical numbers inside of this interval, right? From 1 to 2.5, and right there, in that interval. And then we have to say if the critical numbers are relative minimum or relative maximum or neither. Okay, now remember, critical points or critical numbers, points mean that we have f prime is equal to 0 or f prime is undefined. And yes, you need both, right? They could happen, critical numbers could happen or could occur at either of these two, where f prime is equal to 0 or f prime is undefined. So you need to consider both. Now our work is a bit simplified because f prime would be undefined where the denominator of f prime would equal 0, right? If this equals 0, then f prime would be undefined. But this equals 0 means the quadratic inside the parentheses equal to 0. So for f prime undefined, we need 2x squared minus 7x plus 5 to equal 0. Now, a factored version of this quadratic would be 2x minus 5 times x minus 1 equals 0. And so that'd say that x equals 1 or x equals 2.5 are the critical numbers we'd get from f prime being undefined. But if you're paying attention, those two critical numbers are barely outside of the interval given, but they are outside of the interval given, right? We exclude 1 there, and we exclude 2.5 there. So basically what I'm saying is, like, while it's important when you have a question about critical numbers that you consider where f prime is undefined, you could, in this particular case, ignore these two critical numbers because they fall outside of the interval of interest. Yeah, okay, so we only need to consider where f prime is equal to 0 in this particular case. So where f prime is equal to 0, since f prime is a rational function, right? Since f prime is a rational function, the rational function equaling 0 means the numerator is equal to 0. So we just need to worry about where that's equal to 0. So this implies that we need to look at where negative 3 times 4x minus 7 equals 0. And this could only happen if 4x minus 7 equals 0, which is where x equals 7 over 4. Yeah? Okay, cool. Now, this is just us finding our one critical number in this interval, right? We still need to decide if it's a relative min or a relative max. So to do that, we have to do the number line analysis, right? So like we draw a number line for f prime, right? And I'll do this in black. So we draw like a number line for f prime. So this number line is for f prime. And then we put our critical number on this number line. So x equals 7 over 4. And then remember our interval is just that. So let's say 1 is right here, and then 1 is right here, and then like let's say 2.5 is right there. So in this interval now, we need to test a point to the left of 7 over 4 and then to the right of 7 over 4. By test, I mean we need to pick a number in here and plug it into f prime, and then we need to pick a number in here and plug it into f prime. To the left of 7 over 4 and still fitting in this interval, I think a good point is like 6 over 4 or like 3 over 2, right? So I'm saying figure out what f prime of 3 over 2 is, right? Okay. And then to the right of 7 over 4, we should look at like, say, f prime of 2, right? 2 is clearly to the right of 7 over 4. I'll write that a little bit further to the right. I need the space. So we need to look at f prime of 2 and f prime of 3 over 2. One of them is to the left and one of them is to the right of 7 over 4. We know f prime of 7 over 4 is 0, right? But you'll find that f prime of 3 over 2 is greater than 0, while f prime of 2 is less than 0, which means our function went from increasing to decreasing, which means that this critical point is a local max. Yeah, local max. So you might have to write in words some of what I've just said, but yeah, like write out. But yeah, like yeah, you should get maximum points even if you just have what I have written in part B. Yeah, okay, cool. Keep watching parts C and D to come. In this part, we have to evaluate this improper integral or say that it diverges. And we've got a lot of help from them in that they've given us the partial fraction decomposition of f of x. And this is the decomposition, yeah? All right, cool. And we know that it's easier to integrate this version of f of x than that, yeah? Okay, cool. We'll keep that in mind. All right, but otherwise, we go that from 5 to infinity of like f of x dx can be written with good grammar as like limit as a goes to infinity of the integral from 5 to a of f of x dx, right? And then like we said, we're going to use this version of f of x, so what we just wrote down is same as limit is a goes to infinity of integral from 5 to a of 2 divided by 2x minus 5 and then minus 1 divided by x minus 1 dx. Now, if you so chose, in this part, you can write two different integrals, one for this and then one for that, and then, yeah, proceed that way. But I'm going to keep it just like it is. And one tip is like, if what you find hard is this particular antiderivative, then you can like make a u substitution where u is equal to that. But it's pretty easy. So I'm not going to even show the details of how to find these two antiderivatives, the antiderivative of this and that. So I'm just going to get right into it. So we're going to have limit as a goes to infinity of, and then it will be like the natural log of 2x minus 5, right? And that's for the antiderivative of that, and then it will be minus the natural log, and then minus the natural log of, and then it will be x minus 1, and then of course we need to evaluate both of these at a and then at 5 and take the difference before we evaluate the limit, right? So I'm having trouble writing a vertical bar. There it is. So at a and at 5, and then we'll take the limit as a goes to infinity, right? Once we've evaluated these guys at a and 5 and taken the difference. Okay, cool. Now first let me make this simpler or more succinct by using a log rule. We can use what's called the Cogent Rule, and I recently made a video of that, so you can check that out. But the Cogent Rule for logs allows us to write this simply as follows, which is we can write ln of absolute value of, in my videos on the on logs, I even explain why you need the absolute value, so check that out. But yeah, ln of absolute value of 2x minus 5 divided by x minus 1 is what we can write instead. And I like this, it's simpler, right? And then of course we still need to evaluate at a and 5. So when we evaluated a, well, first we still need to write limit as a goes to infinity, but yeah, when we evaluated a, we get the natural log of the natural log of 2a minus 5 divided by a minus 1, right? And then when we evaluate at 5, we need to take the difference between evaluating at a and evaluating at 5, remember, and hence that minus sign. But yeah, when we evaluate at 5, we're going to get the natural log of, that's 10 minus 5, that's 5, and then 5 minus 1, that's 4. So ln of 5 divided by 4. Okay, now when we evaluate this limit here, right, when we take the limit as a goes to infinity, this here does not have an a, so it remains intact. And in here, what's affected by that limit most is this quotient here. And this quotient, remember, when we're considering a values that are very big, subtracting 5 and subtracting 1 don't matter, right? They're insignificant. Sorry. So then this quotient here is going to be dominated by the ratio of 2a to a, which is 2. So basically we're saying the limit is 2, right? The limit of this is 2, and therefore we'll have ln of 2 in this part, yeah, once we've evaluated the limit. So our final answer is going to say ln of on that end, it's going to say ln of 2 minus ln of 5 over 4, but using the quotient rule one more time, we can write that that's ln of 2 divided by 5 over 4, and therefore it's ln of 8 over 5. Yeah? Okay, so ln of 8 over 5. Okay, cool. Since we are able to evaluate the integral, it does not diverge. Yeah? Okay. Part D here, and it's kind of silly that they asked this question, because while you can decide whether or not the series right here converges or diverges based on other tests, for example, the limit comparison test or direct comparison test, being that in part C, you had to find the value of this integral and you were able to evaluate this integral, clearly you're going to use the integral test to justify the convergence or divergence of this series. And what you're going to say is that by the integral test, since this integral converges, so does this series. Yeah? Okay, cool. All right, keep watching. Problem 6 to come.